Hi everyone, and welcome to this final lecture of week 4. So today we want to talk about how we can simultaneously diagonalize two operators, and simultaneous means two things at once. So let's say I have two operators, one is denoted with omega, another one with lambda. Okay, let me change the color and write it again. So you have two operators, one is omega, another one is lambda. The question is, can we find such eigenbases? Find some eigenbases. This is such that omega and lambda are both diagonal in that basis. This is the question and we are asking. So let's try to find out the answer. And for starters, we are going to assume that this is part 1 of our answer, and then we'll see another part, and these two parts will complement each other. So part 1, let's assume there exists some eigenbasis where omega and lambda are simultaneously diagonal, and this will mean that there exists a simultaneous eigenvector. Sorry, not A over here. Vector of omega and lambda. So mathematically this will mean, let's say I have a vector like V over here, and this is a simultaneous eigenvector of omega and lambda. So if you apply omega on V, let's say it gives you a eigenvalue omega and returns the V, and if you apply lambda, capital lambda that is, over V, it will give you small lambda, another eigenvalue, and it will just rescale the vector. So what does this mean? This means if you apply omega and lambda in this order, that is, first there will be lambda, and second there will be omega, and then you apply V. So first you can do this operation that is under this parenthesis. So this will give us omega, and using equation, let's say this is 1, this is 2. Using equation 2, you can write it as this lambda, which is just a scalar. Let's enclose it with a parenthesis, and this will happen because of equation 2. And since this lambda is just a number, you can just pull over here, and there is omega and V, and then by equation 1, that is using equation 1, we can have lambda omega V, right? Let's call this equation 3. And if you now do this lambda second and omega first over V, similarly enclose this one first. So this is how you should operate it when you have operators. You want to take the one that is on the left of the kit, and you want to go so on and so forth. That is omega first now, then lambda second. If you had another thing, that would be on third, and so on. So now this will give us capital lambda, that is my operator, small omega, and V. But small omega is just a number, so we can write it as this. And then using equation 2, that is this one, you can write it as omega lambda V. And these are just numbers over here, right? In both cases. That is this one and this one. So these two are the same thing. So what does that imply? That implies, let's say this is equation 4. 3 and 4 implies that lambda omega V is equals to omega lambda V. So if there exists such eigenvectors that are eigenvectors for both of these operators, you can say that omega lambda is equal to lambda omega. In other words, lambda and omega, they commute. So here what we did here is that we first assume that we can simultaneously diagonalize them, because we are finding one such basis where both of these matrices are diagonal, or both of these operators are diagonal. And if we assume that, finally we arrive at a conclusion. To satisfy our diagonalization thing, we need to have this condition as well, that is, they have to commute. So this is the condition that is emerging from requiring that we have some eigenbasis where both of these matrices are diagonalizable, and that gives you the condition for commutativity. So if it didn't commute, it wouldn't be possible to diagonalize them simultaneously. So let me just comment this out. Comment or a remark, whatever you want to say. So let me just comment it out, and this means that if two operators are simultaneously diagonalizable, then they will commute. Now what if we start in the reverse process, that is first, so this is part 2. So the first, assume that they commute, that is omega lambda commutator is 0. So now let's try to see what happens when you apply both of them together on in one of the eigenbases. That is, let's say this V is a eigenbasis of lambda, so V is a eigenbasis or eigenvector. Let's write eigenvector. So this will give you omega times small lambda and V, right? Alright, and now since these eigenvectors, and note that we are assuming omega and lambda are non-degenerate. So the reason we are assuming that, because it's quite easy to do it when there is no degeneracy, and when there is non-degeneracy, that is, there is no degeneracy at all, for each of the eigenvalues we get a unique eigenvector. So that's the reason for this, and each of those eigenvectors are equivalent up to a scaling factor. That is, you can actually scale the eigenvectors. That's it. So if you look at this equation, let's call it equation 4, or okay, you know what, let's just call it equation 1, since I think I'm losing track of how many equations I have. So if you just think of it like this way, that instead of the vector V, this vector, sorry, so now think in terms of, instead of V is a vector, let's now think of this lambda V as some V prime, right? You can think of that. Or let's just say instead of lambda V, let's think of it this way. Let's just write down another line first so that it will be easier to understand. Since this small lambda over here is just a number, just pull it out and write omega V, and there is a reason I'm enclosing this parenthesis over here. And since they commute, so you can switch the order without any problem. And now notice something. This omega v can be written as some v prime, right? And here you will have a v prime as well. Alright, so finally what we are getting is that lambda v prime is equals to small lambda v prime, right? So this v prime, that is omega times v, is also an eigenbasis for the lambda operator. But here we have said that lambda is a non-degenerate operator and v is a eigenvector of lambda. But since they are non-degenerate, they have to be unique, right? Let's say instead of lambda you had 2 over here, and this v prime and this v will only differ by some scaling factor. That's the logical thing to do, because if it gets deviated from v, it's not eigenvector anymore, right? So let me just write a summary of it. That is, we are seeing that lambda v prime is equals to lambda v prime, where v prime is now omega v, but we said that lambda v is capital lambda v is small lambda v, right? And for this lambda over here, this v and v prime, so v and v prime, since there is no degeneracy, notice that this is a very important assumption that we are taking. So since there is no degeneracy, this v and v prime are equivalent up to a scale factor. So this is the punchline. And after you say that they are equivalent or equal, so let me also write equal up to a scale factor, so you can finally write it as v prime as some scale factor. Let's call this small omega or anything you want. Let's not write small omega because you might get confused about that. I'm deliberately trying to prove that it will also be an eigenbasis of omega, so let's write it as a. So this is my scaling factor now. Now put the value of v prime as omega v as this, that is on the left hand side, capital omega v, and on the right hand side you have what? The v vector, that was the eigenvector of the lambda operator, and our scaling factor a. But this is just the eigenvalue equation for operator omega. So let's write it down. So this equation mimics the eigenvalue equation for operator omega. So what is happening? The thing that is happening is that when we assume that they commute, that these two operators commute, and we took v as the eigenvector of capital lambda, and we did some algebra over here. After that we saw, and we also assumed that these operators are non-degenerate. So finally we came to a conclusion that this v is, so let me just write it down so that you can recall it better. The conclusion is that v is also an eigenvector for omega or of omega. So finally we can write, if these two operators commute, then they share the same eigenbasis or same eigenvectors, and they are simultaneously diagonalizable. And if you have already forgotten why I'm calling them simultaneously diagonalizable, because remember, we can make a matrix diagonal, let's say omega prime, where this is the diagonal thing, as S inverse omega S, and for lambda prime, let's say, and both of these are diagonal, and S inverse lambda S, let's say. And these two S's in both cases will be the same, because the eigenvectors for the omega and lambda, whenever they commute, is same. So that's why we are calling them simultaneously diagonalizable. And this will be it for today. From the next lectures, we will try to deal with functions of matrices, which will provide very useful when we do calculations in physics and high energy physics, string theory, quantum field theory, and all that. So thank you.